My name's Harriet. I hack your AI so the bad guys can't. Hello everyone, welcome back to episode 4, and today we're talking about adversarial machine learning. Now, I've touched on adversarial machine learning a few times already, but these concepts deserve their own video. Now, this one's going to get a bit mathy, but don't worry, the intention of the math is just so that if you're having a conversation with a machine learning practitioner or a data scientist or a mathematician or statistician, you know what kinds of terms they might use, as well as how to describe and iterate on some of these methods yourself. Now, according to CSET at Georgetown University, which stands for the Center for Security and Emerging Technologies, in 2021 there were 344,000 journal papers, articles on artificial intelligence, for which machine learning is the main driver. Now, this speaks not just to the hype around artificial intelligence technologies, and there is a lot of hype, but it also speaks to the academic interest in novel capability, improvements, and applications. So not all machine learning is going to be as complicated as GPT-4, the model that underpins ChatGPT by OpenAI, but by 2020, reports indicated that every industry had adopted at least some kind of artificial intelligence technology. Now, naturally, as machine learning gained momentum and interest, so too did the kinds of capabilities that could disrupt, deceive, and disclose important information from them. And this evolved into the field of adversarial machine learning. Now, it's important to note that the idea of hacking an algorithm has existed as long as those algorithms had, for example, evading a spam filter in the early 2000s. But the key difference between that and adversarial machine learning is that AML exploits inherent characteristics of ML architectures and characteristics. And this includes, but is not limited to, things like the loss function, the training process, reliance on training data, weights, its black box nature, and different convolutional layers. According to CSET, there were 17,000 papers published on adversarial machine learning between 2010 and 2021. Now, this might surprise you, especially if you haven't heard of adversarial machine learning before. And it's certainly not as many as those papers in artificial intelligence, but it is a lot. And these measurements end in 2021, but I can guarantee that it's just exploded since then as well. So we've talked about AI security a lot, obviously, and AI security is the field that refers to the technical and governance considerations that secure AI systems from attack. This is again where security between AI for security and the security of AI is important, because there are lots of terms that refer to offensive capability of AI, terms like counter AI, offensive AI, adversarial AI. And generally when those terms are used, they're used to refer to AI doing bad things. However, sometimes they are also used in terms of attacks on the AI itself, and it really depends on the context. However, adversarial machine learning is the only term that specifically refers to attacks on ML systems themselves, and it also refers to specific technical practices. It's a little bit like the difference between AI and machine learning. AI refers to a lot of things we would like to make work. Machine learning refers to the specific techniques that actually allow the goals of AI to happen. But the limitation in the field of adversarial machine learning is that it is predominantly an academic field. It's not really a practitioner-led field. And that's not a bad thing at all. However, the actual connection between the research going on in adversarial machine learning and the practical application of it is where it does tend to have the most challenges. So you can think about adversarial machine learning as the academic field that is leading the way in offensive AI techniques. But we need to make sure that there is actually transferability of that research into the practitioner space for both attackers and defenders. Szegedy and Goodfellow were the first to apply adversarial machine learning techniques, at least in the way that this field defines it, in 2013, and they demonstrated the proverbial adversarial machine learning example. Anyone who knows anything about AML has probably seen this example before, and it shows that a panda with specially crafted adversarial pixels added to the image can be misclassified by a model as a gibbon, with a pretty high accuracy. And they did it using a technique called the fast gradient sign method, and I'll talk more about that later, but take note of the term gradient in there. So after this was demonstrated, many examples soon followed, such as glasses that could evade facial recognition, a 3D printed turtle that would be classified as a rifle no matter at what angle it was rotated at, and looking at things like adversarially created stop signs. to defeat autonomous vehicles. What's interesting about this method is that even though it's crafted on images, it's actually surprisingly easy to translate to other data types and domains. Trading, finance models, banking, social media, video and deepfakes, healthcare accounting, network intrusion detection, all of these different fields. It's because most machine learning models are pretty data agnostic. And while there's a lot of work that goes into the pre-processing of data to make it fit the model architectures themselves are often pretty similar regardless of the data. So these kinds of adversarial machine learning methods are highly transferable, especially when most machine learning systems are very brittle. It was found that it was pretty easy to cause a misclassification with minimal effort. So since the field of adversarial machine learning exploded in 2014, there are now at least over 100 different types of attacks. You can see these listed in MITRE's Atlas matrix, which is their database of TTPs, tactics, techniques and procedures for adversarial machine learning techniques. You can also go to repositories like ART or the Adversarial Robustness Toolbox, or others like Clever Hans. So these repositories list dozens and dozens of different attacks, and then if you factor in all the different techniques that pop up in academic papers, which are often based on existing methods but tend to extend them in some way or customize them in some way, you've got a massive landscape of different attack types. So here I'm going to go into some of the popular methods, and I am going to show you the mathematical equations here, and that's not to bamboozle you with math, but it's to expose you to what these kinds of equations look like, and for those of you who are more mathematics inclined, to then be able to understand and extend on them yourself. So the first method is universal adversarial perturbations, or UAP, and it's basically a really fancy way of saying random noise. So this technique basically means that you're adding a perturbation vector, and we call it a vector because it's really just a large array of numbers that is then added on top of an image to an entire image that alters each pixel for each image by a unique value. So what that's saying is that it is totally independent of the actual target model itself. It is literally random noise. The aim is that this vector be small enough to be unobserved by humans, but significant enough to fool the classifier. This technique really exposes the brittleness of most models. Maybe you wouldn't call it an adversarial machine learning technique, but it is important to include in any benchmarking that you do around machine learning systems, especially when comparing them to adversarial machine learning attacks, because if you attack models but the success rate isn't much greater than adding random noise, that says much more about the ML system itself and how robust or not robust it is than about their specific attack. So it's important to note UAP here. So the first proper adversarial machine learning method is the one we referred to earlier, the fast gradient sign method, or FGSM. And the fast gradient sign method was first proposed by Szegedy and Goodfellow in 2013-2014, and this method calculates the gradient of the model's loss function relative to the input. So what does this mean? Basically, whenever you're training a machine learning model, you have a loss function. It's telling you how much accuracy you're losing. And this is the goal that a machine learning system is trying to work towards. So the way that this technique works is by identifying what that gradient or loss function is, and instead of trying to make it more accurate, you're making it less accurate. And the way that you're doing this is by changing the input data. You're adding the adversarial pixels to the image, but they're specifically crafted based on the target model because you know which areas of the image to perturb and in what way to cause an incorrect classification. So in a lot of demos, this is the technique that you'll see used because it's pretty computationally inexpensive. I mentioned that it is one shot, and that basically means that the actual adversarial pixels you're adding to the image are generated using one training iteration. And this is fast, it's easy, it works most of the time, but it would not be the optimal pixels to add to that image. So the next technique is called projected gradient descent, and it basically solves the problem of non-optimal one-shot perturbations by extending this technique to make it iterative. So basically, instead of adding adversarial pixels using one iteration of this method, you would conduct multiple iterations. So it becomes more refined and more likely to cause a misclassification, but less likely to be observed by a human. It is still constrained in an epsilon value, which basically means that if you could change the image in a dramatic way, it's going to cause a misclassification. But you want to reach that point where it causes a misclassification, but it's not obvious to the humans. And that boundary you set is called the epsilon value. And in math, epsilon just refers to any small number typically, but you would see that as the value of epsilon increases, there's more likely to be a misclassification, but the human can see it pretty easily. So you have to find that point where it's a balance between the two. Okay, the 1 pixel attack. The 1 pixel attack also uses an iterative approach, so you change 1 pixel by different colors, and then you do that for every pixel in an image, and you see if there is one specific pixel that is able to cause a misclassification. And for some images and for some models, this can work pretty well, but it doesn't necessarily work all of the time. So you would call this a brittle technique, but it is still worth mentioning here just to highlight that in some use cases, changing 1 pixel can actually work quite well. So now we have the adversarial patch. And the adversarial patch is another image which, when placed near or on the target object, causes the model to ignore the actual object in the scene and instead report the chosen target of the patch. So a good example of this is a patch that is able to defeat people classifiers. So if someone wears this adversarial patch, they can't be detected, or this toaster patch. So if you place this patch near an object, the model instead looks at the patch, predicts a toaster, and ignores the real object. Okay, so I know that now obviously there are many more techniques, like the Carlini and Wagner method. There's other kinds of attacks that are better for specific use cases, like time series data, for example. And if you want to have more of a look at them, head over to the resources that I've listed here, but I will also be doing specific episodes dedicated to these techniques later. But if there's anything I want you to take away from this, it's that for all of those techniques, I discussed things like optimization. I talked about gradient functions, loss functions. When we talk about adversarial machine learning, it's exploiting characteristics inherent in machine learning architectures. And number one is optimization. So not every technique will exploit optimization, but many of them do. And this is certainly where the field started. Now, in machine learning, you need to optimize because that's how a model learns. It's optimizing over many iterations to go from a random model architecture to weights, activations, and biases in a model that are able to steer the predictions in the correct way. You need to give a model a goal, which is typically accuracy, and you need to give it a way of tracking that goal, which is the loss function. And so from an adversarial perspective, if you know the information about the loss or the gradient function, you're able to see what about the model makes it accurate, and then you're able to unpick what about the model would make it less accurate. A way that I like to think about this is using this image, and it makes sense to me because in a machine learning system, we're basically trying to find a higher dimensional plane, the combination of activations, weights, and biases that will make the model perform best. And when you start with random values and then they are being updated over time to make the model more accurate, it's almost like you're walking down this loss function to find the global minima. And so when I talk about stepping up the gradient, it basically means that you can understand what about that image you need to change to cause a misclassification. And you want those values to be able to cause a significant enough misclassification, but balanced out with the ability for humans to detect it. An analogy is to think about a hill. If a hill represents the loss function, and the goal is to find the lowest point on the hill, this represents the global minimum. The slope of the hill represents how quickly the loss function is changing, and optimization algorithms can be thought of walkers that are trying to find the lowest point on the hill. The walkers start at a random point on the hill and then take steps in the direction of the steepest descent. This means that they are always moving towards the lowest point in the hill. The process of moving up the slope is akin to taking a mower or an earth mover, but I'm obviously no expert in land clearing, to the hill and sort of reshaping it, so that not only is the path down the hill slightly different, but so is the rest of the hill. Now, adversarial machine learning attacks can occur at every point in the machine learning lifecycle, and those high-level attack classes include poisoning attacks, extraction attacks, evasion attacks, and inference attacks. I believe a systems-based approach to security should always be considered because AI systems typically include many interacting machine learning models and different software systems. You could further categorize AML attacks by the adversary's knowledge, specificity, attack frequency, and objective. and the adversary's knowledge of the target model is referred to as either white, grey or black box. So white box presumes the attacker has full knowledge of the internal characteristics of the target model, which includes model weights, training data or the loss function. And on the other end of the spectrum, black box means that there is no knowledge of the target model and is usually assumed to be the state of the real adversary, unless you have an insider threat, but that's usually pretty unlikely. Grey box refers to some point on the continuum between white and black box where some of the characteristics of the target model is known. Attack specificity refers to what extent an adversary has a specific outcome in mind, so you want that panda to be misclassified specifically as a given. A non-targeted attack might aim to disrupt the model's behaviour but without an explicit outcome. So adding random noise to an image that just reduces its overall accuracy. These characteristics and the continuum for each can be used for threat modelling to determine the impact of adversarial machine learning attacks on a target given contrasting adversarial capability. Despite the multitude of attacks, there are many categories of machine learning that have yet to inspire attacks or be investigated for target or threat analysis. So in a future blog, I'll go into more depth on the range of defenses against adversarial machine learning techniques and how they can be employed in a practical sense. But key to note is that there are a number of defenses that can be employed, and some are extensions of existing cybersecurity controls, whereas others are more specific to the machine learning lifecycle and architecture of specific implementations of AI systems. The defensive field is broad, with many other potential defenses that focus on defense against specific attacks or distributed approaches that spread risk, but my argument is that instead of positing the AI security field as one of attacks versus defenses, it really needs to be more about risk-based mitigations. This is why, in discussing the security of an AI system, we focus less on the technical defenses that could be put in place, but rather on the needs of the ecosystem to enable and mature the practice of AI security. This is changing though, and I've been so delighted by the progress I've seen in the academic and practitioner community. However, there is still a long way to go. So we've discussed how different cybersecurity controls can be used against adversarial machine learning attacks. So in the next episode, we're going to be doing sort of a cybersecurity 101. So things that you might not know about cybersecurity, and specifically in how they can be applied to AI security. Okay, and now it's time for the AI joke of the week. Why did the AI break up with the chatbot? Because it felt like it was just talking to itself. Okay, please like, comment and subscribe, and I'll see you in the next episode.